actually the same exact graph as the previous one, but this time we're writing the exact function as opposed to a possible function, okay? As best we can. So the key difference here is that on this function, you're given this point right here, 420. So we're going to use the same exact idea as we did last time, where we wrote a possible graph, except now what we're going to do is we're going to solve for the leading coefficient, the a value, which we didn't in the last case. So here, same information applies, right? So just real quick, we have a root at x equals -5 with multiplicity 3. We have another 0 at x equals -1. This one has multiplicity 2. And then this 0 right here at x equals 3 has multiplicity 2 as well. And remember, 3, 4, 5, 6, 7. It needs to add to 7 since this is a degree 7. So the only difference between this rule that we're going to write and the one previously is that now we have to figure out this a value, right? So what we like about that is we have this point xy, and we can use that point, plug it in, substitute it into this equation. So x goes into all the x's, y goes into f of x, and we solve for a. A will not always be a nice fraction, but the one thing we can do to check our work for this one, or at least know we're in the right direction, is that the right end behavior of this curve right here, right? As x increases, it's going up towards the positive y direction. That means our leading coefficient, a, must be positive. This number must be positive. So if we end up with a negative value, that means we probably made a mistake. So what we're going to do is we're going to substitute 420 into our polynomial, solve it for a, and as we work it out, we end up with a equals 4 over 3,645. Leave it as a fraction that's simplified, and we're going to substitute that into the a value and just leave our function as is here. And that's an exact equation given the information, assuming that it's multiplicity 3, 2, and 2 for the given zeros, x-intercepts there. And that's it for this one.